All right, so one related to the master set, and then a toy.
With 5 ohms, yeah. And then you're aiming for 1.7 plus or minus 0.2 amps.
Plus or minus.
0.2 amps.
All right, so the general, I'm gonna change the numbers here,
Yeah.
because this is the master set problem, but I might change it into numbers that won't work, I don't know.
So there are numbers that just don't work. Well,
Yeah, I mean, if this were 100 ohms right here, then probably it'd be very difficult to
Yeah.
hit that target.
What's about the process anyway?
Yes. Let's make that 8, and let's just see if it works.
Okay.
So there's more than one technique. What I'm going to do is just go over a type of approach. So first off, my power supply, we'll make it 15 volts. Again, don't know if it works yet. So we have 15 volts, and this is my target. So first thing I would do is try to figure out what is the equivalent resistance. And sorry about that, Millie. Let's pull this out of the way for now. So my equivalent resistance times the current coming out of the power supply is equal to the voltage of the power supply. So basically, Ohm's law. So 15 is equal to I times, and I'm going to target the exact middle. That gives me a little bit of leeway in case it doesn't quite work out perfectly. I have had ones where my R value that I actually ended up using was one of the extremes as opposed to smack dab in the middle. So, and it helps if I actually put things in the right place, 1.7 times R. That's my equivalent. So the equivalent resistance I'm looking for would be 15 over 1.7, which is something. So it'd probably be about 9.2 unless someone wants to come out.
Point.
8.8. All right, now it's a whole lot simpler if I have my power supply here, and the current coming out of it is the same as, basically the current coming out of it is the same current that goes across my toy. So then I've got some mystery resistance here to complete my circuit. Well, if I need 8.8 ohms and my toy is 5 ohms, that means that this right here, since I have this in series, has to be 3.3 ohms.
Yeah.
Or 3.8, the way you kids do math today. 3.8 ohms. So I now have 4 resistors, one of which is variable, and I'm trying to hit 3.8 ohms. Well, that 8 definitely can't be in series because I need it to be smaller than, actually smaller than those two right there. So somehow I need to have something in parallel. So I'm just going to start out and just try something. So if I take my 4 and my 8 in series, and then I put the 3 there, and just see what I get. So that is a 12 and a 3 in parallel. So 1/12 plus 1/3 equals 1 over that equivalent resistance, Rx. So doing the fancy math here, that is 4/12, so that's 5/12. So my equivalent resistance is 12/5, which is 2.4 ohms. And I'm trying to get 3.8 ohms. Well, the difference here is 1.4. So I could just then stick R here and make it 1.4 ohms because it's within the allowed range. And done. If it had not come out nicely like that and I needed to drop it down a little bit more, then I could have put the variable resistor somewhere in this path here. And, you know, there is a certain, it's an educated guess that you're doing here.
Is there any reason you started with the 12 and 3?
I knew that my resistance needed to be, for the remaining 4, my resistance needed to be under 3.8 ohms. So I just took the 2 that were bigger than that and stuck them together in parallel with something. That was my thinking.
Okay. And it just happened to work out that way.
Yeah, usually it doesn't work out the first time. It usually about 2 or 3, sometimes 4, 5 times 4 it works out. Typically when I design these problems, I sort of make up the 3 node resistors here. I come out with a circuit, throw in my variable resistor of a certain amount, and I basically work backwards. And then I see that there is a solution. Hoping I have not made a careless error. And then present the problem, sort of. And sometimes you get a variety of different answers that all work. The biggest mistake I see is what people are searching for is the 1.7 amperes coming out of the power supply, not going across the toy. So, for instance, if the toy were here, that the current splits. Yeah. So whatever's coming out of the power supply is not coming out, going across the toy in this case.
So you would, most of the times you would like the toy at the end of the circuit.
Or the beginning, yeah.
Yeah.
That's the way I do it.
And is it usually easier to save the changeable resistor till the end after you?
Personally, yes, I find that true.
Okay.
I'm sorry.
Thank you.
That's said. Ish.
But if we have the 4, 8, and 3, which makes the 12 of the 3, which gives us our 2.4 ohms resistance,
Yes.
then we add one more resistor of 1.4. Oh, we still have to have the 5 to make the 8. Okay,
Yeah.
I get it.
Is there only one right answer for this?
Yeah.
One? No?
No, I mean, I come out with an answer. As I start grading things, I go, oh, that works too. Okay, and then I start writing down all the things that could have worked.
Do you want me to wait to ask this after class? But I did a different one of this. Just can you look at it and tell me? Do you want to do that? Can we do that after?
After.
Okay.
So, when solving the 3 battery problem, I don't want you to go through the entire thing, but I was asking as to, like, I did the 2 loop method and then the middle up and down thing. Because
The 2 loop method and the up and down thing.
I came out with the 2 equations.
You did mesh it, 2 equations.
Mesh analysis.
Okay.
So I got the 2 equations and then using the accounting for both of them.
In the middle, all right.
Arrows in the middle.
So you had I sub A plus or minus I sub B.
Yes. And so I have the current 1, 2, and 3. From there,
Wait, why do you, okay, keep going.
from there, what exactly are you supposed to do with those 3 currents?
Well, the question is, what is the current go out across each resistor, and then what's the potential difference across one of the resistors?
Yes. So I have to find, so for example, if I found the current in this loop,
Right.
I could use that current to find
Right. Okay.
what's going off here,
Yes, and there.
and there, and there. No, there
Well,
would
that
be.
has a combination of those two.
Yeah.
I'm assuming your 2 equations did not have an I3 in it.
No.
Okay.
So yeah, so this would probably have to do with this.
So that is, you have your I1 and I2,
Yeah, I1, I2.
and they are going in opposite directions here.
Yeah.
So it would be the difference, okay, so you took that into account. Wait a second, oh, you have two negatives there, one negative there, okay.
So, with that, that's the, like, I could use each of these separately to find each of the,
Yeah.
okay. Cause I was like, wait a minute, like that, cause, yeah, something wasn't clicking in my head.
Apparently it was.
There we
I
go.
had another question, just quick. One of the other master set questions was with 3 light bulbs and varying brightnesses because they're resistors and you connect them differently. Does brightness change on how much, I guess, current is going into it?
Yes,
Okay. So more current means brighter
yes,
till it blows up.
yes, exactly.
So, if something requires less current, which means it'll be less bright, does that mean it'll also last longer?
If you're comparing it to another identical bulb,
Identical bulb means,
it should,
because it's not drawing as much from the power.
yeah, it's not burning up the material
Okay.
as fast.
So, is the power delivered by the battery the same as the power received by each bulb?
No. No, for instance, in this particular example, the power delivered by the battery, I delta V, there's my current and my voltage is 15, so I just multiplied that. That's the power delivered by the power supply. The power across each bulb, well, I could still use the same equation, or the I squared R, or the, let's see, delta V equals IR, or delta V is, or I squared over R. Yeah. For each one specifically, so that has a resistance of, so, that's not how I wanna do this, but if I figure out the current flowing across that bulb squared divided by that resistance, that'll tell me the power lost by that resistor. So, if I use it with R equivalent and the voltage of the power supply, then I'm doing the power supply is producing. If I do it for an individual resistor and the current flowing across that individual resistor, or the voltage across that individual resistor, then I'm doing it for that specific resistor.
But if it's from the battery, it's over the whole thing?
Yeah. And in theory, whatever the power supply is producing, should be matched by the total power lost by the individual components.
Yeah, because so the battery produces power. If you add more resistors, wouldn't the power just get spread out and not actually decrease?
How do you add it? So if,
Series.
so I got a power supply here, and I have a resistor. So I have a power supply and a resistor. And so the power generated here would equal the power loss here. If I added another resistor like that, yeah, the power loss would,
Just be spread out, but it would stay.
well, it's also gonna generate more power.
Because it has to do more to spread.
It has to do more in this case, so the current coming out of the power supply increases.
Well, why would it have to do more? Because wouldn't that be less resistance?
If I've got, let's make this a 12-volt battery and a 3-ohm resistor, I'm gonna have 4 amperes flowing across that. I got 4 amperes flowing across out of here.
Yeah.
Now I add a resistor in parallel. And let's make it a 4 ohm resistor. So I will have 3 amperes flowing across that. So if I have 4 amperes, 3 amperes flowing across it, that means I now have 7 amperes flowing out of the power supply. In order to either keep both of these lit or have both of these resistors for whatever purpose they are, I need to draw more power from this.
Wait, did the 3 amperes come from, where did that?
That 3 amperes, because if I do my voltage loop here around like that, I gain 12 here, I have to lose 12 there. So I lose, so I have a 4 ohm resistor, it has to be 3 amps. I don't know if I've answered your question or not.
No, you have, yeah.
Okay. Now recognize that the nice thing about this design though, even though it draws more power, is that if that resistor blows, this resistor is still working. We still have a circuit, assuming that this doesn't, well actually the current would drop off, so we would go back to what it was before we added that. But if I did a series here, so if I had my 12 volt, and then 3 ohm and 4 ohm, I have less current coming out of the power supply. However, if this blows, the circuit's dead. And this works with a string of lights. I always think of Christmas lights, but it works with any string of lights. That if the lights are in series, in theory, you don't need as much current. It saves power, but if one blows, you have no idea which one is out. But if they're in parallel, if one blows, well, you know exactly which one is out. And then, but it takes more energy to do it. Now, I think the current design is you have a group, you tend to have a group in series, and then you'll have another group in series. So that if that goes out, you just lose half the lights, but we still have some lights left.
Now, just as a question, if like the third light in that second strand that you already marked off went off, would you know it's that third light, or just the whole strand go out?
The whole string goes out, and you then have to go through the painstaking task of checking each bulb or if you got nothing to do, you pop a light out, pop a new one in. Hope that the light that you're putting into that place actually works. Other questions? All right, just a reminder. Homework quiz and master set, 21.